In this video, we'll now discuss forces. From our everyday experience, we know that a force is a push or a pull on an object. It turns out that the idea of a force is not so intuitively obvious as you may think. We'll come back to discuss that later on when we talk about fictitious forces, non-inertial reference frames, as well as Einstein's idea of the equivalence principle. But for now, we'll leave with our intuitive nature that we have as a child, that when you push or you pull something, that is the application of a force. Now, physicists study forces because they're fundamental in our discussion, as we talked about in Newton's first law. So we've tried to identify different types of forces. And if you get down to trying to understand what causes forces and where they go, at everyday temperatures, we see that there are basically 4 different types of forces. One force is the gravitational force. It has certain properties. For one thing, it is attractive and never repulsive. It is infinite in its range. No matter how far you get away from something, you're still attracted by its gravity. We know the cause of that. The cause is mass. We'll come back to that idea later on. And it's relatively weak. Now, it has lots of applications. Of course, we could talk about weight. If you don't consider the weight of a building in civil engineering, that would be a serious mistake. But it also helps form cosmology and the way our universe actually works. Now, one of the neat things about gravity, like I said, is it's always attractive. So no matter what anybody may tell you, everyone's attracted to you. Even when you get very close to a person that says, "Oh, get away from me, I don't want to be around you, you're repulsive." You're not repulsive, you're attractive. And the more you eat and the bigger your mass, the more attractive you actually become. Now, that brings us up to the next force. If you get too close to people, they will provide the electromagnetic force and slap you. And that can be repulsive. So it can be both attractive and repulsive. It is also infinite in range. And its cause is charge and moving charge known as current. And we won't study that in this section. We will study that next semester. Electronics is an example of this. Light, magnetism, radio, television, numerous applications. This is the most dominant of our everyday experience. Almost everything about you, whether you write on a tablet, the process of writing is actually electromagnetic. Walking across the floor is electromagnetic. Almost everything you do, eating food is electromagnetic. Almost everything you do in life is an electromagnetic interaction. Now, we have some others. We have what's called the strong nuclear force. And while in fact this thing is like 20 orders of magnitude stronger than gravitation, the strong nuclear is an incredibly strong force. However, it's very short-ranged, on the order of only a femtometer. And it's always attractive. And we know what its cause is too. It's caused through what are known as gluons between the things. But we'll go back and talk. It's much more complicated, and we're not going to deal with it in this course. Things that it does, it holds the nucleus together. But it does more than that. It also is important in radioactive pharmaceuticals, and it can be useful for nuclear reactions, which we can use to make nuclear power. So nuclear power, nuclear weapons. Whoops. etc. There's also the weak nuclear force. It's short-ranged, but it's repulsive. And it causes things like decay. But without the decay and the heating of these type of forces, there wouldn't be life on this planet. Without decay, you can do positron emission tomography, medical applications. So it has an extremely important practical applications in its own right. Everything is composed of those four. Now, it turns out that if you turn up the temperature much greater than where we live every day, we'll find something really interesting. We know that at least 3 of these forces are actually different aspects of a single force. Those 3 being electromagnetism, the strong force, and the weak nuclear force. We have not yet been able to connect gravity, but that may very well be close to doing it. We believe that these are actually same different aspects of this single force, in the same way intelligence, humor, sadness, there are different aspects of your personality. Now, I said that we haven't done gravity. In order to combine gravity, there would have to exist a particle called the Higgs boson. This would break what's called the Higgs field and give particles their unique masses. We believe that we may have found the Higgs boson this last summer, in which case we may be on our way to understanding the nature of gravity. We can turn electricity on and off. We control the power of the strong nuclear by nuclear reactions, and we make elements that we want to do medical applications, generate nuclear power, and even be destructive in the case of weapons. But we don't control gravity. What if we could control gravity? Turn it on, turn it off. Turn on your mass, turn off your mass. Without your mass, you couldn't actually experience a force in a car collision. You couldn't be killed in a car collision anymore. You wouldn't have to have any great force to shoot payloads like satellites into outer space. You'd be able to pick them up and throw them up. You could float ceilings of buildings. We can't control that with a switch like we can electromagnetism. But if we understood where gravity comes from, maybe we could. And so this could be potentially a huge breakthrough. We in general, in physicists, believe that we will eventually find something like the Higgs boson, because we believe that the world is really much simpler than the way we see it. We just don't understand the rules of the game. And eventually we will find the unified field theory that explains all forces. There are really only 2 things: understand forces and understand masses. What does it mean to have matter, and what does it mean to have an interaction between matter? If you understood those, you would understand every field from medicine to engineering to anything that there is in the universe. If you understood those. And that's what physicists, at least some physicists, that's what they spend their time attempting to solve. Now, while these are totally true facts and they're fundamental to physicists, they're not going to be what you find most useful for solving your problems. So let's get to some things you need for your problems. Newton was a hugely influential person, so they ended up naming the unit of the force after him. A Newton is a kilogram times a meter per a second squared. Now, don't name any units after me, because for one thing, it makes it difficult to do dimensional analysis, and now everybody has a unit named after them. There's a joule, there's a watt, there's an amp, there's a coulomb, there's a volt, there's a farad. I mean, there's a Henry. We named all these things after people, and students have to remember what they are. And second, you have to be dead to have it named after you, and I don't plan to die right away. We also decide not to classify forces based upon this idea of electromagnetism, gravity. What we prefer first is to define them in terms of how they work with Newton's first law. Newton's first law says you only need to know the external forces. So we should break forces into internal forces and external forces. Internal forces are the forces inside a particle, or even more generally, the forces inside a particular mass of what's called a free body diagram that we'll learn about later. These forces do not affect the overall motion of the body. So, Newton 1 says you don't have to know the internal forces to predict the motion of a bridge. Alternatively, Newton 1 says that a particle can't change its own motion. In other words, you can't grab yourself by the seat of your pants and fly. That only happens to the Lorax in cartoons. What you need to know is the external forces. These are the forces outside the particle, and they're the ones that can actually cause the object to accelerate. So what we're wanting to do is we're going to want to draw something called a free body diagram. We're going to draw an object. The forces that are caused by things outside, like the earth maybe pulling down, those are important. But any forces inside, in here, they don't count. Only the forces coming from things outside can affect the motion. Alright, that's enough for this video. We'll come back and talk about how we want to classify these external forces in order to ensure that we never forget any of them, and what a free body diagram is in the next video.